Okay, so let's again start with a warm-up. So here we're trying to find the general antiderivative for the function 2x times the square root of x squared plus 9, which might be quite a bit more complicated than a lot of the functions that we've been integrating so far. So what you should think about when trying to come up with this antiderivative is what would happen with the chain rule when you took the derivative of something, and then try to find what the antiderivative would be, take its derivative to check to see if it's correct. So go ahead and pause the video and try to work on this warm-up. I'll do the solution for it in a second. Okay, so hopefully you could find that antiderivative. Let me go through this. So the first thing that we notice for the warm-up is that the derivative of the inside function in this composition of functions where we have the square root and x squared plus 9. So the derivative of x squared plus 9 is actually equal to 2x. So we've got this set up as composition of functions, but the derivative of this inside function is sitting right out here being multiplied just like it would if we took the chain rule of some derivative. So we should be thinking, okay, we can probably just forget about the fact that this is composition of functions and just treat it as a square root of something and take the antiderivative of that square root. So our guess would be that we can have our antiderivative. We'll just use capital F of x for the general antiderivative here. That's going to be, well, let's just take x squared plus 9 and do the power rule on the power of 1/2 for this. So increase the power by 1, we'll get 3/2. And then divide by that new power, 3/2, and then we can just flip it up and write it as multiplication by the reciprocal. It'll be 2 times x squared plus 9 to the 3/2 divided by 3. And plus c, we wanted the general antiderivative. Let me get him in there too. Okay, so let's check it. All right, so the derivative of our general antiderivative will multiply by the power up front. Oh, let me start here. So that'll be 3/2, and then we just write the 2/3 up front also, times 2/3. And then we'll decrease the power by 1, so that'll give us our half power, x squared plus 9 to the half. But now we have a function inside of that power, so we've got to multiply by the derivative of the inside to use the chain rule, so times 2x for that derivative of x squared plus 9. So just cleaning all this up, all of those guys will cancel. We can write this 2x out front, that looks a little bit better. So it'll be 2x times the square root for the half power of x squared plus 9. Which is exactly what we started with, what we wanted to find the antiderivative for. So this looks like our general antiderivative. Okay, so it's really nice to take the antiderivative of something where it's composition of functions, but you have the derivative of that inside just sitting out there. It works perfectly with the chain rule. So this seems pretty clear, but it actually can be helpful even in situations where it's not as clear that we can write it as exactly a function times its derivative, or composition of function times the derivative of the inside function. So in general, just looking at what we did before, we can do a substitution when we've got a composition of functions and the derivative of the inside function just sitting on the outside being multiplied. Then it's just the same as doing the antiderivative of the outside function of the inside part, just calling it a variable u, and doing the antiderivative and then substituting the rule for the inside function back in at the end. Okay, so just to make this a little bit more clear, what kind of the g of x is and how the u comes about from it. Let's just do the warm-up again, but using that notation that we have from that formula. Okay, so let's start by writing it as an integral just to match what we have for our substitution rule. So for our warm-up, we'd be looking for the integral of 2x times the square root of x squared plus 9, this indefinite integral dx. And to match the notation that we have in the substitution rule, what we're going to do is let g of x equal x squared plus 9, that inside function in this composition. And f of x will be the outside function, the square root function, so just square root of x. And then with that, then we know what g prime of x is. That's just the derivative of g of x, so that's 2x. Okay, so it's pretty clear that this integral is set up exactly like the left side of the substitution rule. So we could write this as exactly that left side. It would be f composed with g of x for this part, the square root of x squared plus 9. And then times g prime of the x for this 2x, just to put it in the same spot as the g prime of x in the rule, times dx. Okay, and then the rule says that this should be equal just to f of u du, so we just have to do that antiderivative of the outside function and then substitute in for g of x at the end. And then just to show how we're going to do it for more complicated examples, what we normally do is say that u is equal to that inside function, g of x, and then take the derivative of this equation. This is kind of shorthand, but it allows you to make sure that you're setting up the for the substitution for the integral in terms of u the correct way. So taking the derivative of u will give us du, and then taking the derivative of g of x will be the same thing as g prime of x, and then we write dx like we're doing the chain rule on x inside of here, and that's just to make sure that the substitution works out correctly, because we're supposed to be getting from the substitution rule, we should be getting that this is equal to f of u du. So to just make sure that we're getting this correct, we take the derivative, and the derivative of u we write as du, and then the derivative of g of x we write as g prime of x, but then think about it as like using the chain rule times x and we get a dx out there on the end. Okay, but then this shows a nice substitution where g prime of x dx gets substituted in as du, and produces that integral of just the integral of f of u du. Okay, so unpacking this all and just doing the antiderivative. This will be the integral of f of u, but f was the square root of x, so it'll be the square root of u du. But we can take that antiderivative, just increase the power on u by 1, be u to the 3/2, and then divided by 3/2, so multiply by the reciprocal, 2/3, plus c. But then originally we were given a function in terms of x to integrate, so we should write our antiderivative in terms of x also. So just plug back in for what we called u. Here we've got to kind of go through two substitutions but it's just x squared plus 9. So that'll be 2 times x squared plus 9 to the 3 halves divided by 3 plus c. Okay, so that's just showing where all of this kind of comes from. So you always set u equal to the inside function, and then figure out what du is in terms of dx, make that substitution, and then compute the integral. Okay, so let me do a couple of examples. I won't use as many g's and f's as we did here. I'll show kind of the streamlined process for it. But we'll see that it might be a little bit more complicated than the one we had, where it's not as clear that you just got the function, the derivative of an inside function sitting out there, but we can kind of tweak it to make it that way. Okay, so for the first example, our composition of functions is in the denominator here. So when we're trying to find out this integral, even though the derivative of x squared plus 1 isn't exactly x, we can make it into the right derivative if we just kind of multiply or divide by a constant in order to get 2x, which is the derivative up there on the top. Okay, and you can do this in that scratch work where you set the inside function equal to u. So we've got composition of functions, so you use u substitution and set u equal to the inside function. And now to figure out what the integral is going to be in terms of u, we have that du is going to be the derivative, going to take the derivative of both sides of this equation, is going to be 2x for the derivative of that inside function, but then you multiply by dx using the chain rule to make sure this is set up right. Okay, but before we had exactly g prime of x dx to substitute in for, but now we're looking for 2x dx to get du, but we only have x dx. So we can actually correct this by just dividing both sides of this equation by 2 and getting that 1/2 du is going to be equal to x dx, which we do have. And this is the same as just multiplying by a half out front, and then multiplying by 2 inside. You'd still get the right antiderivative. You'd have 2x here and just pick up a factor of a half. But you can see it in this notation that we would pick up a 1/2 du for x dx and make that substitution. Okay, so as long as we have that, we can now take care of all of the x's by substituting and get an integral just in terms of u. So we can write the half out front. It's just going to be a constant that we're multiplying inside of the integral. And let me actually write that in there so you can see the substitution a little bit better. Okay, so how this is going to work is we'll get the integral of x dx is going to be a 1/2 du. And x squared plus 1 is now u, and it's squared. Okay, and then in this notation, it's really just multiplying by du on the end. So if you have du in the top of a fraction, it's still just the integral. So this will be 1/2 the integral of du over u squared, which is just the integral of 1 over u squared. So we take this antiderivative by using the power rule. We'll get increase the power by 1, so from -2 up to -1. So we'll get -1 and divide by -1, so it'll just pick up a negative, and we'll get -1 over 2, and then u is going to be to the -1 now, so just u in the denominator, plus c. Okay. Oh, sorry. So like I said before, it's getting late, so I'm probably messing up here. You were given the function in terms of x though, so we don't want to just leave this in terms of u. We've got to then make the substitution back in where u is equal to x squared plus 1. So this will be -1 over 2 times x squared plus 1 plus c. Okay, now we're done. Sorry about that. Okay. All right, so then for the next one, this can also be thought of as the integral of cotangent dx. Okay, so yeah, this is the integral of cotangent, which is cosine over sine. But written in this way is where you can see the composition of functions. So it's really the reciprocal function, 1 over sine x. So composition of 1 over x and sine x. That's what we're going to be undoing. So we want to set sine x equal to u, that's inside function. And then the same way that we did it before, take the derivative of both sides to see what the substitution is going to look like. So du is going to be the derivative of sine, so cosine x, and then use the chain rule for dx. And now we can see that we have exactly cosine x in our integral, so we can substitute cosine x dx in for du and write our integral just in terms of u. I'm also substituting in u for sine. Okay, so with that substitution, this will be the integral of, for x dx, that'll be du in the top. And then sine x is going to be just u. Now we have a nice antiderivative to take in terms of u, so it's just the integral of u to the -1 du. So if it were a power rule, we'd increase it by 1, we get 0. So remember that this is the natural log antiderivative. So this will be the natural log of the absolute value of u. And we took the antiderivative now, so we pick up a plus c. And then don't forget, like I did last time, to substitute back in for x at the end. So this will be the natural log of the absolute value of sine x plus c. Okay, so the antiderivative of cotangent doesn't turn out to be really all that nice. In order to get all of the values that we can plug in to cotangent, we need to be using the absolute value of sine x plus c. So it's kind of a really strange antiderivative for what seems like a kind of simple function, cotangent. Okay. All right, so let's try one more example where we've got to, instead of finding a indefinite integral, find the definite integral and see how that works when we do a u substitution. Okay, so we want to do the integral from 0 to 1. At least we have nice numbers for those limits of integration. Of 6x squared times 1 plus 5x cubed to the 5th. So before, if we wanted to do this, we'd have to expand all of this out and then distribute. It would be really ugly. We definitely want to multiply that together with 5 copies of it. So, but what we can tell is that we've got composition of functions, and it looks like the outside looks like exactly the derivative of the inside. So this should work. What we're multiplying on the outside looks exactly like the derivative of the inside. So it looks like this should work really nicely for u substitution. So set u equal to the whole inside. You don't want to leave any part of the inside out. Don't just use u as 2x cubed. We want the whole inside to be u. U equals 1 plus 2x cubed. And then du is going to be, the 1 doesn't give us any derivative. Multiply by 3 for 6x and decrease the power by 1 squared, and then multiply by dx just to make sure the substitution works. Okay, so we do have a 6x dx to substitute in for du, and then the 1 plus 2x cubed is going to be u inside of here. So when we make all of the substitution, we've got to be careful because these limits that we had were x limits. So the integral is from x equals 0 up to x equals 1. So don't mistake them as u limits. We'll see how to kind of switch them next, but for now let's just remember that they're x values that we've got to substitute in after we get the x antiderivative. Okay, so then the integral is going to be the 6x squared and the dx are taken up for du. So just in here will be u to the 5th. And then the 6x squared and the dx become du. And we can take that antiderivative. So we'll get u increase the power by 1 to 6 over 6 evaluated from x equals 0 up to x equals 1. But now we've got to put the substitute back in for u. To get x for our antiderivative, and we'll get uh, 1 plus 2x cubed to the 6th over 6 evaluated from now. We have it in for x, so we can plug in 1 and 0. Okay, so what we'll get is when we plug in 1, we'll get 1 plus 2, so 3, to the 6th over 6, to the 6 over 6, and then minus plug in 0 for x, so 1 plus 0, so 1 to the 6th, 1 to the 6 over 6. And in the end, we'll get 3 to the 6, which is, sorry, let me check my notes here real quick. Which is, let me just check it here real quick. Which is 234 over 6 minus 1/6. Let me just make sure that's right. Oh, sorry, that's 729. I was gonna say, And I've got an even number there. Okay, yeah, so 3 to the 6th is 729 over 6 minus 1. So we'll end up with actually 728 over 6. So we should be able to get a 2 to reduce there. So we end up with 364 over 3 as a value. Okay, for the exact value there. Okay, so we could have actually done this a little bit faster. Instead of plugging in 1 and 0 to this antiderivative in terms of x, we could actually just switch these limits to u limits and plug them in terms of u. So we can see that because this value that we got here, 3, is exactly what we'd get if we plugged in our top limit 1 for u. We'd get 1 plus 2. So this was exactly what we'd get if we plugged in 1 for x into u, into the u function. And this 1 is exactly what we'd get by plugging in 0 for x into u, if we treat it as a u function. Okay, so we could have actually just done this as a limit from u equals 0, from u equals 1 up to u equals 3, and wound up getting exactly this once we did evaluated this from 1 to 3. Okay. So that works in general. You can actually, if you use a substitution again as u equals g of x, so let's do this again as g of x. Then we could have actually got these limits by doing g of 1 plugged into our u antiderivative, and g of 0 plugged into our u antiderivative. Exactly like it says here. So we'll get g of a to g of b of f of u du. Okay, so let's try a couple of examples like this. And then you just have a few exercises to do, which again I'll post the solutions. But let me get through these examples. Okay, so now we've got definite integrals. For our first one, the integral from 0 to 2 of e to the x over e to the x plus 1 dx. Okay, so the composition of functions here is this 1 over x squared plus 1. So we want to set u equal to that inside, e to the x plus 1. And then we should see that we've got exactly the derivative of u sitting up there, so this should work really well. So it'll be u du, taking the derivative of both sides, is e to the x stays the same when we take the derivative. The 1 doesn't give us anything, and then multiply by dx for the chain rule. Okay, so this e to the x and dx will be du, great. E to the x plus 1 will be u. We should be able to write this in terms of u really easily. But we can also write the limits in terms of u. So let's just switch these limits to be u limits by taking x equals 0 and figuring out what u is when x is 0. So when x is 0, we get e to the 0, which is 1, plus 1, so u is 2. And when x is 2, we get that u is e to the 2 plus 1, which we can't really simplify, so we've got to unfortunately just leave that as e squared plus 1. So, substituting everything in, we can write this all just as a u integral, a u definite integral. So it'll be the integral from 2 is our new lower limit, up to e squared plus 1. And now our new integral is e to the x dx is now du, and that whole denominator is just u. So it'll end up being equal to, our antiderivative is just the natural log of the absolute value of u. Everything's positive here though, so we don't need the absolute value. It'll just be the natural log of u, evaluated from 2 up to e squared plus 1. Okay, and we'll end up getting the natural log of e squared plus 1 minus this with 2 plugged in, the natural log of 2. Okay, and we can't really do too much to simplify that. We can't break up addition with the natural log, but we can put the subtraction together in the same natural log and maybe make that look a little bit better. We can say this is the natural log of e squared plus 1 just over 2. Subtraction becomes division inside of the natural log, and that's, I think, really about the easiest we can do for it. Okay, and let's just finish up with the last one here. So this one, the limits didn't make it too much easier, but for the next one, it does make it pretty nice. Okay, so for our last example, we'll be doing the integral from e up to e to the 4th of dx over x times the square root of the natural log of x. Okay, so this one's a little bit more clear where the composition of functions is. We definitely want to set u equal to the natural log here. And then remember, the derivative of natural log is 1 over x, so we need that x to be in the denominator in order for that to work out. So we're lucky that it is. That will be what will work as our derivative of natural log. So we want to set u equal to natural log of x, and then du is going to be equal to natural log, the derivative of natural log is 1 over x, and then again multiplied by dx for the chain rule. And then we'll have dx over x or 1 over x dx, but both of these will be taken care of by du. And of course this natural log will just be u. So now let's switch our limits. So when x is e, for our lower limit, u is going to be the natural log of e, which is just 1. And when x is e to the 4th, u is going to be the natural log of e to the 4th. But remember, the natural log just asks you e to what power is the value that's in the natural log. So e to the what power is e to the 4th? Well, that's just 4. So we'll end up getting much nicer limits for this. It will be, with all of that substitution said and done, it'll be the integral from 1 up to 4 of the x in the denominator, and the dx become du over the square root of natural log of x, which is u. And that takes care of everything, and we get that new integral. and that's much better to take the antiderivative for. So it'll be u to the negative 1/2 du. So just the power rule, increase the power by 1 is positive 1/2. I don't need a denominator in the end, so u to the positive 1/2, and then multiply by the reciprocal, so multiply by 2. So it'll be 2 u to the 1/2, or 2 square root of u. Evaluated from now the u in values 1 to 4. So we'll end up with plugging in 4 first, so it'll be 2 square root of 4 for just 4 to the half, and then minus 2 square root of 1, so it'll be 2 times 2, so 4 minus 2, and give us 2 in the end. Okay. All right, so try the next slide, which is the exercises on your own. So some of them are definite integrals, some are indefinite integrals. So remember, for an indefinite integral, like the first one, you should end up with a family of functions. And for the definite integrals, you should end up with a single value. And I'll again post the solutions to this either tonight. It's getting pretty late, so probably not. But when I get back then, or if I have time to do it at the hotel, if I can copy them in. So, okay, so yeah, we'll see you on Thursday. Hope that you could understand these videos and follow along with the examples and see how to work through your homework. So it was a little hard without people to ask questions. So, all right, well, you guys have a good couple of days, and I will see you.